In this lesson, we'll learn about uncertainty. Uncertainty is a very important topic for all practical units. So, physics unit 3 and 6, chemistry unit 3 and 6, biology unit 3 and 6 as well. Uncertainty is basically the inaccuracy when we are taking a reading. For example, if we measure this, so we have a box over here and I want to measure the length of it. So I'll place a ruler next to it and then measure it. Now when I use a meter rule over here, so this is a meter rule. In this case, the values are given 1 millimeter apart in the meter rule. So if I zoom in and see, so I'll place it next to the 0 line and I'll take a reading over here in this case. However, if we keep zooming in and into the object, so this is the marking on the meter rule. Now if my object is shaped like this and it ends in the middle of this, so this is in the middle, I'll take an approximation. So in this case, I'll either take this value as the reading or this value as the reading. There is an inaccuracy crossed over here since there is no marking over here. No instrument can really measure this length exactly. So this is an uncertainty caused over here. This uncertainty is dependent on the resolution or precision of the instrument. The resolution or precision basically means how fine a measuring instrument can read a detail. For meter rule, the precision or resolution is 1 millimeter. 1 millimeter is the smallest value that a meter rule can measure. So the resolution or precision, resolution and precision are the same thing, and it means that it's basically the smallest change in a quantity that can be recorded by this instrument. So for this case over here, the smallest change in a reading that a meter rule can measure is 1 millimeter. Some other examples are 0.1 millimeter for vernier calipers and 0.01 millimeters for micrometer screw gauge. There are also other instruments. Now in the case that we don't know the resolution or precision of an instrument from beforehand, we can use the value it's giving. So for example, if I'm given a mass of 23.43 kilograms, the resolution of the instrument will be 0.01 kg. This is the precision of the instrument or the resolution of the instrument. This will be the smallest value. You go to the smallest place value of the kilograms. So in this case, the smallest value it can read is hundredths or 2 decimal place after the point. So this is 0.01 kg. If the weighing balance was better, it could read more decimal places. For example, it could read values like 432 kg. In this case, the resolution or the precision would be 0.001 kg. If the instrument was slightly less accurate, you could also have 23.4 kg. So the resolution is even worse over here, it's 0.1 kg. So this is what you use if you don't know the resolution of the instrument from beforehand and you're just given the values. Now that was resolution and precision. Now we have to learn how it's linked to the measurement uncertainty. The measurement uncertainty basically means the range where we can find the exact value. Now for this example, if this was so this is 15 millimeters. Now since we know that the measurement uncertainty, or since we know the resolution of a meter rule is 0.1 millimeter, I could either take the next value or the one in before, or if we saw in the example, if this was our scale and our reading was this, we can either take to the left or to the right. So this reading plus or minus half the resolution. This is the uncertainty over here. So the measurement uncertainty is usually half the resolution or precision. I say usually because we'll learn about some exceptions over here. So there are two types of reading instruments we'll have to deal with. One of them are double reading instruments, and the other are single reading instruments. Double reading instruments are instruments like the meter rule, for example. One of them is the meter rule. Another would be a digital balance or any weighing balance. It doesn't have to be digital, any weighing balance. It can be a burette as well. These are double reading instruments. Some single reading instruments would be vernier calipers, micrometer, screw gauge. Thermometers can either be double reading or single reading. Now double reading and single reading, the difference is when we are measuring something with a meter rule or weighing balance or a burette. So I'll start with the meter rule first. So if I have a meter rule and I want to measure the length of something with this, so I want to measure the length of this. Now if I want to measure the length, I'll place this near 0. So I have to align this value. When I have to align this value, there is one uncertainty caused over here. And when I have to check this value over here, another uncertainty is caused over there. So the measurement uncertainty must be multiplied by 2 in this case for double reading instruments. Weighing balance might be a surprising inclusion in this list, but for the weighing balance, when it's showing 0, the force on it is not actually 0. The weight of the atmosphere is on this. The balance is actually measuring the difference in masses. So for this, it's measuring 0. And when you put something on it, then it's measuring another weight. So it's measuring the weight twice. It's measuring the mass twice. So you can also think about the tare function. So if you place something on a weighing balance and press the tare button, it will reset to 0. So this is the new 0. When you have this container over here, the reading shows 0. And if you add something to the container, the reading increases and becomes a positive value. So when we first had the 0, there was some uncertainty in the measurement of this container's mass. So there is the uncertainty being added twice. So we have to do twice the measurement uncertainty in that case as well. And same for burette. When some liquid is flowing out of it, I will first look at the initial height of the liquid. So I'm measuring this height once and then the final height another time. So I'm measuring two values. So there will be two uncertainties involved. In vernier caliper and micrometer screw gauge, that issue is not there, because we don't have to set the zero value over there, it's set automatically. So for double reading instruments, we make the zero value, we set it, while for single reading instruments it's already done for us, the zero reading is set for us. The difference in calculation would be that for single reading instruments, so I'll do single reading instruments on the left, double on the left and single on the right. For double reading instruments, the uncertainty can be considered to be equal to the precision, while for single reading instruments, the uncertainty will be half the resolution or half the precision. Now this is for uncertainty. We'll have to learn how to calculate percentage uncertainty as well. The percentage uncertainty is given by this formula, which is the measurement uncertainty divided by the measured value. This will be divided by the measured value, and then we multiply it with 100. Now we are given this question about finding the percentage uncertainty in these values of time, 30.1 second and 70.4. From the readings, we can see that the resolution is 0.1 seconds. By using the fact that the farthest value or the smallest place value is 1/10, so 1/10 of a second is the resolution, so the measurement uncertainty will be half of that. And if we divide it by the measured value, which is 30.1 for the first case, and multiply it with 100, we get the percentage uncertainty for 30.1 second. And if I just change the denominator to 70.4, I get the percentage uncertainty for the second value, which is 0.07%. From here we can see that for the same measurement uncertainty, a greater denominator will mean that the percentage uncertainty is smaller. Having a smaller percentage uncertainty is better. Now we do this if I didn't know the instruments that were used. However, if I was told that this was done using a stopwatch, for example, I'll have to multiply 2 over here and 2 over here. This is because stopwatch is another double reading instrument. Stopwatch is a double reading instrument because you have to manually start it when you see something. So for example, if I was measuring the time it takes for a ball to slide down a ramp, and I'm given 2 markers over here, so a ball is sliding down the ramp, I start the timer when it crosses the red marker, and I stop the timer, or I stop timing it when the ball rolls down to this blue marking. So this is the stop point and the red one is the start point. Now in both cases I am starting and stopping this. So this is one point where I use the timer. So this is one of the point where an uncertainty is caused, and when I stop the timer there is another uncertainty caused. So we are taking 2 readings. The start point is measured by us manually, and the end point is also manually measured by us. So a stopwatch is a double reading instrument. If I didn't know that this was done using a stopwatch, I'd treat it like a single reading instrument. However, if I knew it was a double reading instrument used, so stopwatch for example, I'll multiply 2. Since we weren't given that this was done using a stopwatch, we'll not have to do it. So you have to remember that if we are not told that if we do not know the instrument, we'll assume that it's a single reading instrument. So we take this assumption when we work with uncertainty. Now, what we learned before for uncertainty was if we take a single reading. Don't confuse this with a single and double reading instrument. A single reading, basically, for this case, I'm referring to the fact that we are measuring it once and not taking any repeats. But if I had a repeat, for example, for 30.1 second, instead of just having 30.1, if I had 29.9, 30.0 and 30.4. So if I did 3 repeats of the same value, now the uncertainty would be calculated by using the range. At first, we'll have to find the average value for these 3. So the average value in this case will be 29.9 plus 30.0 plus 30.4 divided by 3. Now in some cases we are also given anomalies, so we have 3 readings that are close together and we'll have another reading which is far away from them. So if I had 4 readings and one of them was 25 out here, which is very different from the other values, this will be ignored as an anomaly. Over here, the average value comes out to be 30.1. In this case, the percentage uncertainty is half of the range of values. The range is the maximum value minus the minimum value divided by 2. The range is the maximum minus minimum, and then we divide it by 2, and then the whole thing is divided by the average value. And then you multiply it with 100. So for this case, the maximum value is 30.4, the minimum is 29.9. We divide it by 2 and divide the whole thing by 30.1 and multiply it with 100. From here we get the value of the percentage uncertainty. When we have repeats, this will be 0.83%. So for repeat, when we have repeat values, we take half the range and use that instead of the measurement uncertainty. So when we have repeats, so in cases where we have repeat, we'll replace the measurement uncertainty which we use usually, and instead of that we use half of the range. So the maximum value minus the minimum value divided by 2, half of the range. And that's how we get the percentage uncertainty when we have repeat readings. Now, if the repeat readings were like this, so all of the values were 30.1, in this case the measurement uncertainty would be 0 if I use this formula, since the range will be 0, the maximum minus minimum value is 0. So in cases like this, if I have repeat values that are giving us a small percentage uncertainty, I'll have to go back to this. So for repeat readings, if this uncertainty over here using maximum minus minimum is greater, I'll use this. However, if this is smaller than the single reading uncertainty, which is 0.17 for 30.1 seconds, I'll use this. So if our values were close together, so 30.05, 30.15 values really close, the percentage uncertainty we'll get from this equation or this formula over here will be very small. So if this was smaller than 0.17%, instead of using this formula, the one we usually use for repeats, we'll have to use the one that we use for non-repeat cases. We have to use whichever of this or this is larger. So the larger value of the percentage uncertainty should be used between them. And that's it for uncertainty.